So in my title, I of course have the words fundamental physics, and it requires some definition because presumably every one of these speakers, if they were talking about their subject, would say that's fundamental physics. So I just have, and that would be reasonable, but the definition that I'm using here is the physics which is at the intersection of the two pillars of our subject, quantum mechanics and relativity. Okay, so that's what I mean by fundamental physics. In the talk, I'm not trying to necessarily take one particular topic. I'm trying to give you a sense of the grandeur of that subject, and something that's harder to do, so I will attempt to do it, is to give you a sense of the beauty of the subject. Not just that it's a bizarre and whiz-bang kind of world of fundamental physics, but there's something that is actually strikingly beautiful about it. There's a lady who happens to have a T-shirt or sweatshirt saying, "Without geometry, life would be pointless." And I think I can just tell you the talk is...
I don't happen to have the T-shirt. I wore it for your talk.
Oh, thank you. So I wanted to amplify it. Actually, without geometry, life would be impossible. Or the universe would be impossible. So that's what the talk is about. It's certainly about the possible role of higher dimensions of space-time that could be playing out in nature in some disguised way, and about the experiments that might hope to uncover their role in the coming years and decades. But also, the subject is so bizarre that if you were to understand even what we've learned so far, you would find that to convey it to somebody else, you would be speechless, because English does not have the words to say what we have already seen, let alone what we might see in the future. The least bizarre way of tackling some of these subjects is through thinking about the role of extra dimensions. They are the most visualizable of these bizarrely unspeakable principles that I want to talk about. So the extra dimensions play two roles. One, they allow us to imagine what would otherwise be only spoken in the language of mathematics. And they also might actually be there and playing a hidden role, and I want to tell you about that. Okay? So I didn't get into this subject. I didn't get into physics because my love-hate relationship with this subject didn't start as a kid by doing math problems or math puzzles or playing with chemistry sets. Instead, as a kid, I was very much taken by the ancient mythologies, the Norse mythology, Greek mythology, Indian mythology, and for me, that was fundamental. It talked about the beginning events of all time, the beginning of the universe, the making of everything, and in that, there was a big role for the forces of nature, which were all incarnated as demigods, right? So they were the central characters. And so it's quite a surprise, once you're a professional physicist, to see that, in fact, there is a kind of family tree that we are slowly starting to piece together for the forces of nature. And they are indeed governing our lives. They are like the demigods of old. The most data that we have, the strongest representative of the tree is indeed the youngest of these elements, the last children, if you like, the strong, weak nuclear forces, electromagnetism, and gravity that you learn about in high school. But they have ancestors, like the electroweak force, which we're now exploring at the Large Hadron Collider. There are strong indications that there's an even grander parent, the sort of grandpa force, and then maybe an ultimate mother force where there are mathematical indications, but encapsulated in, say, superstring theory, but less experimental evidence. And then beyond this particular family, there is dark matter, dark energy. These dark forces are out there. We know much less about them, but we have experimental evidence. I'm not going to talk about them very much, even though that deserves a completely separate public lecture by some master of the dark arts, which I'm not. Okay? So you may think that this family tree does not have what we see in real family trees, that you have two parents and their DNA gets exchanged in some way and then get the children. In fact, that's only because it's sort of a family lecture. But indeed, in the details, say, of this, there really are two parents that are exchanging their DNA and giving rise to 2 children. I've just suppressed it. Okay, so this is what I want to talk about, but I want to talk about the ideas, but I also want to talk about what experiments can hope to do to grasp all of these things. So, all of you know that 100 years ago, Einstein developed general relativity as the modern theory of gravity. It incorporated, at least at an approximate level, Newton's inverse square law of gravitation, which is wonderfully in accord with experimental data certainly 100 years ago. But it had small corrections which made it consistent with the, at that time, newly discovered laws of electromagnetism. In particular, the laws that related to special relativity, that the speed of light, electromagnetic radiation, is the same for all observers, which when one thinks about it, is actually a kind of bizarre statement. That the speed of light is not infinitely fast, which is our experience of it, but it's actually a finite speed, and it's the fastest possible speed that anything can have. Okay, so making Newton's laws conform to those basic principles led to general relativity, which, however, looks so vastly different from anything that we had seen before. What was previously the stage for all happenings, namely space and time, now became an actor itself, so that, as you may have seen in these kind of cartoons, where there are massive objects, there is some sort of deformation of space and time, or space-time in its vicinity, and we perceive that as gravity. I thought, why not write equations? What's wrong? If it's a public lecture, what do I care? So here are Einstein's equations. I write them because they have a rune-like beauty, and they are magical, and so we should see them. Okay, so there they are. Now, one of the simplest questions, if space and time curve in some way, is to ask, can curved space allow you, if there is such a thing as curved space, if this is curved space, if me doing this is the result of space-time being curved, which we perceive as gravity, why not take it to the logical limit? Maybe these 2 dimensions are perfectly normal, but could it ever be that, say, I go in that direction and it's a circle, so I keep going in that direction and I find myself walking in this way, okay? Or if you want, the light from the back of my head goes all the way out there and then somehow comes back and hits me in the eye, so I see myself blocking myself, blocking my own view, right? Could that ever happen? Okay, could the 3rd dimension be circular in this way? Well, the evidence would be you would see the back of your head, and or with a very big telescope you'd see the back of your head. There's no evidence to suggest that. Okay, so if it's true, this radius of this circle is somewhere on the scale of the universe. Already I'm using a trick that I'm going to be forced to use, and hopefully most of you will just get it. I have drawn the 2 dimensions that I'm not doing anything strange to. I've drawn it just as a line because I needed more space to draw the possibility that the 3rd dimension is a circle. So this is obviously schematic. And so I've indicated that in your mind's eye you're supposed to think of the vertical direction as representing 2 dimensions, and then this horizontal circle as being the 3rd dimension. So I hope you sort of get that way of depicting things, because we'll be using it a lot. Now you can ask, fine, maybe, so you see in this picture, 2 dimensions are just as we always imagined, and 1 dimension is behaving strangely. It's finite in size. Okay, and we can ask whether, in some sense, even though we have no evidence of this, whether the 3 dimensions that we think are all there is, whether they themselves are but a remnant of a higher space where there's a circle. So that would be this picture, where the 3 dimensions that we think of go in the vertical direction, but there's an extra dimension of space, which is a circle. Now, if this extra dimension, there's a little piece of nomenclature. We have to name it. Now, we have already in special relativity used the name time as the 4th dimension, okay? Because in special relativity, we discovered that there's a little bit of interchangeability between time and space. two different observers will not agree on what is time and what is space, even though in ordinary life everybody agrees on that. It's the more familiar thing in everyday life is we're facing each other and we disagree on left and right, right? He'll tell me, jump to your left. I'll jump this way. And he said, that's not what I meant, right? So we agree on the relativity of that. But the relativity of time and space is something that only is apparent when you travel very fast, but it's true. And so in honor of that, we call time the fourth dimension. So if we have one more spatial dimension, we call it the fifth dimension, okay? And so we're asking, could this be what's going on? That this extra circle is so tiny, it's so microscopic that it's not part of our everyday experience. And then we only see the long dimensions, the three long dimensions. Now, to try and sort of grapple with that a little bit more, it's useful to draw a slightly higher dimensional picture so that we can see more of the usual dimensions and imagine ourselves in this world, okay? Because that's the way to make sense of everything, is to sort of put yourself in this world, because it might be your world, okay? So let's in this case, the extra dimension, the fifth dimension, is a circle. You can see that. What if it, instead of a circle, it was just an interval? Like it was just from here to here, okay? Not a circle. Then we'd draw this picture. Then I can afford to say that we live in a kind of sheet-like universe where the two dimensions along this sheet that I'm showing you really represent three dimensions schematically. And there's an extra dimension, which is an interval. So we live in a kind of sandwich universe where these are three dimensions, but there is an interval in the middle there. And it's so microscopically small that we think we just live in three dimensions, but secretly everything is a little thickened. And here you are, right? Very much like, say, a quarter or a coin, right? The face on a coin. And you're big, but you're big in three dimensions. You're very, very thin in the fifth dimension because it's a very, very small, narrow space, okay? If you ever had an ant farm, I don't know, for people old enough, if you ever had an ant farm when you were a kid, you'd see little ants traveling only in their narrow little space, living a very two-dimensional life. Well, we're living a very three-dimensional life in this little narrow space. And we're even asking questions like, what fifth dimension are we talking about? What are we talking about? I can't even imagine it because it doesn't correspond to anything I've ever seen. And my imagination is just, cutting and splicing what I've seen. Indeed, we can understand why you can't see it. Here's ordinary light carrying pictures to your eyes, and they're traveling in three dimensions. If you want to look in the sideways direction, which is so microscopically small, if you try to look in that direction, you would need light with wavelengths that fit inside this little cavity. But if it's sufficiently small, these wavelengths are so small that they would correspond to ultraviolet light beyond your visual range. And you would see nothing, okay? And indeed, none of you are visually aware of any sort of extra dimension. Okay, so this is how, logically, there could be higher dimensions, but they have something a little bit different about them. They're so small, for one reason or another, they're so small that they're not apparent to macroscopic people like ourselves. Okay, so here's the remarkable thing. You say, what about Occam's razor? Why have you invoked something that I can't see, and then just to sort of get my juices flowing, right? Why have you done this? So here's a payoff, okay? So in the early part of the last century, Kaluza and Klein put together a exercise that you can do. You can take this universe, which is sort of three-dimensional depicted in this vertical direction, and then this fifth-dimensional circle, and you can just study the theory of gravity on it. Now, the theory of gravity is just curved space-time. It's just saying that what you're seeing as a cylinder is secretly something that can dance around, it can stretch, and so on, right? And that's really the theory of gravity in 5 dimensions. But the extra dimension is so small that you can't see it. And so for a macroscopic person, you can ask, what remnant of this higher dimensional gravity survives for macroscopic observers. And you're not surprised that standard gravity comes out. Standard three-dimensional general relativity, or 3 dimensions plus time general relativity, comes out. That's wonderful, maybe expected, because you're blind to the extra dimension. What's remarkable is the 2-for-1 deal, because you also end up with 3-dimensional, or 3 plus 1 dimensional, 3 plus time dimensional electromagnetism. So you only put in higher dimensional general relativity, only higher dimensional gravity, and then you look at what a macroscopic observer would perceive, and they would perceive both gravity and electromagnetism, 2-for-1. Okay? So that's a shock. Maybe then you say, oh, maybe I should take extra dimensions seriously. Einstein was very impressed by this and wanted to take it seriously too. In some sense, the extra electromagnetism comes because there are strange ways of stretching and moving the space-time that come, which involve both sort of twisting and turning in the circle, extra dimension, as well as in the usual 3 dimensions. Okay. So in this picture, electromagnetism is a kind of weird remnant of gravity itself, albeit in a higher dimension. Unfortunately, so I said that, well, why didn't I hear about that? Okay, that must obviously be the theory of the world. And the problem is it's a little unrealistic. So the details didn't work. And here's why. Here is on this axis, I'm just plotting mass. Here is some tiny electron mass on this scale. But the thing that sets the scale is what's called the Planck mass. And the Planck mass is the division between black hole physics and particle physics. If you have a very compact object, and particles are meant to be very compact objects by definition, if they are larger than this Planck mass, which is that many zeros times the proton mass, okay, so something really big, okay, I think it's about a gram or something. But anyway, if you have a very compact object which is that heavy or heavier, then it's no longer a particle, it's a black hole, okay? So the regime of particle physics is below the Planck mass. Otherwise, you're into black hole physics. And so you might say, okay, on this sort of natural scale of Planck mass, where do we live? So we're made out of like protons and electrons. So the proton is somewhere down here. It's obviously not to scale. It's 1 gazillionth of the Planck mass, right? I think I got the right number of zeros. And the electron mass is even lighter. So these are the charged particles you learn about in high school. But the Kaluza-Klein theory, this higher dimensional theory, it's actually very predictive because it's a unified theory of gravity and electromagnetism. It has predictions. And it predicts that the charged particles live close to the Planck mass. They're almost black holes. So this is at odds with the experiment, and so normally you'd say you throw it away. But if you're a theorist, you always try to see if something is salvageable. And there is. So in modern superstring theories, about which I will tell you very little, but in modern superstring theories, they're not yet validated by experiment, but they're compelling. In these theories, the basic Kaluza-Klein mechanism that I talked about, these kind of 2-for-1 like deals, is more or less alive and well, with a few extra gadgets to make them realistic. And so you can have this kind of 2-for-1 deal. Okay, so that's why I'm showing it to you. But I'm also trying to give you a sense of what is so shocking to us. What is it that grabs us physicists, okay, in fundamental physics? We're looking for this kind of fix, right? If we can get unifications like this, then we're happy. We feel like it's like Newton figuring out the moon goes around the Earth for the same reason that the apple fell on his head, right? It's not obvious. Okay. Okay, to go a little bit further, I need to introduce the concept of internal space. Okay? It's very, very easy at the level that I've told you. Here is that cylinder world with the fifth dimension as a circle. And indeed, I'm just defining the internal space as what you get by just taking this space-time and just fixing a particular three-dimensional point, say this blue thing here. I guess I was supposed to be using this. So I just take a cross-section at one particular three-dimensional point, and obviously I get the circle. And so that circle is an example of an internal space. So here it's very easy. It's not worth my defining it. And yet, I'm introducing the rules that determine what forces are macroscopically emergent, okay, to a person who does not see with their naked eye this microscopic dimension. And the rule is that you get a kind of force field for free, beyond gravity, you get a force field for free, for every symmetry of the internal space. So if you give me a circle, then everybody can see that if you turn it like this, that's a symmetry, rotational symmetry, and you get one force field, which is the electromagnetic force field. Okay. Now you can just go to some higher dimensional internal space. So here I'm thinking of two extra dimensions, a fifth and a sixth, and even though I can't draw it, I'm drawing it still as a circle, I'm going to say that the fifth and sixth are really, if I could do a better job, they would be a sphere. Okay. So now I have a two-dimensional sphere, the surface of a sphere, and this is my internal space, and it's microscopically small, and you do general relativity on that. What's going to happen? And the answer is you will get long-range forces which correspond to the different symmetries of a sphere. And as you know, with a sphere, you can sort of turn it this way, or you can turn it this way, or you can turn it this way. And basically, these are the three independent types of moves. And you find that you sort of get three force fields instead of just the electromagnetic force field. And they talk to each other in a very beautiful way. And these are called the electroweak forces. Okay? I should say right now that I am trying to give you the spirit of the law. And occasionally I will violate the letter of the law. And I have no shame about that. But I know there are people in the audience who are physicists and may tear out their hair. The details can easily be learned. So I'm going to say what I just said. Right. So now, and then you can ask, but what about the strong nuclear force? This is the electroweak force. It's actually, if you remember in my ANCESTRY diagram, electroweak was like a parent of the weak and the electromagnetic forces, but not each of them in detail. It's this parent force. And then you can also say, what about the strong nuclear force? And the answer is there's some higher dimensional version of a sphere, which I'm not going to draw, which would have enough symmetry that it would correspond to the strong nuclear force fields, which are described in a theory that is known as quantum chromodynamics. And indeed, the previous director of the KITP, David Gross, is one of the Nobel Prize winners rewarded in that way for putting together this very beautiful theory of quantum chromodynamics, the theory of the strong nuclear force. Okay, so symmetries rule. Now, quantum mechanics, let's put that in. And again, all of you know that there's the idea that for every force field, or at least like the electromagnetic field, is secretly at the quantum level made out of many, many, many particles, photons. Okay, so photons are the particles of light, and they are massless. Okay, so here I'm drawing mass. Here's the Planck mass, the division between black holes and particles, and the photon is way down here, and is the mediator or the particle of electromagnetism. If you look at the electroweak prediction from having a perfect sphere as the internal space, then you find there's a photon and what's called the W plus and W minus particles. Already you see that by some subtleties, by changing the Kaluza-Klein theory a little bit, we do better, because it turns out the W plus and W minus are electrically charged under electromagnetism. So already we've done better. We found charged particles which are not all the way close to the Planck scale. Remember, that was a problem of the Kaluza-Klein theory. Already we've improved on it. We've brought them down to earth a little bit. But still, the details don't match experiment, because this is what experiment looks like. Okay? Experiment has the photon being massless, but the W plus and the W minus being about 100 times the proton mass. Okay? And these are the force carriers of the weak nuclear force. Okay? Much as the photon is the particle of light, these are the particles of the weak nuclear force. And you can see they're way, way down compared to the Planck mass. So in a sense, if you just take off your glasses, this is a device I use many times, and I'm blessed with poor sight. These two pictures look the same, obviously. So this is not a bad approximation. So we're getting close. We're getting close to data, but we're not quite there yet. What you need to do to really nail the slight imperfection of the data, the fact that these are not all sitting at exactly the same mass, is you need to take the perfect sphere of the internal space, and you need to flatten it a little bit, like make it. I learned one word in making this talk. It's the word oblate. I think I'm using it correctly. So you need to sort of flatten it a little bit. And so here is the oblate sphere, just a little bit oblate. And what happens is electromagnetism, the photon stays massless. The W and the W plus W minus, the mediators of the weak force, get a small mass compared to the Planck scale. And that also renders them mediating a short-range force, which the weak force is, rather than electromagnetism, which can be felt very far away. Okay, so we're able to, in this way, nail this. And that brings me to the famous, but not very well understood, Higgs field. And my job was to at least explain a picture of the Higgs field so that I didn't have to say it in any other way. Just draw it, okay? So this is what we call the vacuum. When I draw this picture, nothing much is going on, okay? This is the most symmetric view of it. The fifth and sixth dimensions just doing their own thing, and space, nothing changing from one place to another as you move around in standard three-dimensional space. It's the so-called vacuum, the lowest energy state when there's basically nothing going on. But this is what a Higgs field is. Remember, this is meant to be, this cross-section here is actually not a sphere. It's a slightly oblate sphere. And now you can imagine that with if I gave you a balloon, you could sort of push it in a little bit on one side and then let go, and it might vibrate in some way, okay? So here, this internal space is sort of vibrating and forming a wave that travels in 3 dimensions, okay? So maybe here it's a little less oblate, and here a little more oblate, and here a little less oblate, and here, and so it's just some vibrating membrane that's going along. That is the Higgs field. Okay, that's you asked what's the significance of this thing, the Higgs field? Why did we read about it in the New York Times in 2012? Well, this is it. It's a vibration in this sense. And now, and you say, really? They never said in the New York Times about extra dimensions and okay. So I have to correct something. So the Higgs field, all of the things I've told you, the germ of them is sitting inside what's called the standard model of particle physics. And I want to say, in what sense is the standard model of particle physics related to these beautiful extra-dimensional pictures that I've been showing you? And I think the analogy is when you are teaching one of your children about numbers, you will say, well, imagine 5 chocolates. Okay. Now I take away 2 of the chocolates, and that leaves you with 3 chocolates. And in this way, by giving these examples, which are clearly visualizable, you are teaching also the more general concept of number. Now, number is a wonderful abstraction, if you think about it, because you don't require the actual object. You don't have to say, is it 5 unicorns or 5 chocolates? The 5-ness and the 3-ness are an abstraction, and you can understand it quite clearly. If you are talking to a very small child, and you go through the 5 chocolates, take away 2 chocolates, they're more likely, and you say, have you got the idea of number? They're more likely to say, give me back the 2 chocolates, okay? But we are more sophisticated. So first let me say that what happens here is all of these extra-dimensional theories, the simplest versions that I've been trying to draw, are in detail they're flawed. In detail something goes wrong. And yet we can write a geometric theory that truly is realistic and involves gravity, electromagnetism, weak and strong nuclear forces. We can do it completely realistically. And it's written in the mathematics of external space and internal spaces. Okay, it's the mathematics of those. And yet it can remain agnostic. It's like saying it's the mathematics of chocolates, but I don't declare that I actually have the chocolates, Johnny. Okay? So they can be agnostic as to whether the internal space relates to extra dimensions or not. It's just the mathematics of those. But that is all that we need to actually capture the data. In fact, these theories written in the language of internal spaces, the geometry of internal spaces, is in fantastic accord with an enormous body of experimental data on all these forces. Okay? So at the moment, I've told you what is sort of, if you believe in superstring theories, then these extra dimensions are actually real. Okay? But I want to distinguish theory and theory bolstered by actual experiments. Actual experiments have not actually shown us that these extra dimensions are real, but the mathematics that underlies them seems to be real. Slightly different. 5 chocolates or 5. Okay, that's the distinction. Okay, now, this picture, so when I show you these pictures from now on, let's for at least for the next few minutes, let's keep clear that I'm allowing you to visualize something mathematical that would otherwise be requiring me to write equations. Okay? So there is a kind of problem, a puzzle that we still don't understand, called the hierarchy problem, and it's basically the following. If this internal space, this internal squashed sphere, is very oblate, then what you find is the photon and the force carriers of the weak force, the W's, are very badly split in mass, and the W plus and W minus would actually be much closer to the Planck mass. They'd be closer to being black holes, which is very much at odds with data. Remember, the W is somewhere down here. This is data, okay? And yet, a theory that has this kind of behavior is very robust to write down, okay? As you vary parameters, it doesn't change very much. If you have a perfect sphere, then you have the electroweak unified theory, which looks like this. Again, it's incredibly robust. You can change the parameters a little bit, and our world would not change very much in how it plays out. This situation, which actually matches data, where you have a very, very nearly spherical internal space, turns out to give the data, but it requires the parameters of the theory to be just so. Okay? It's a very delicate, difficult to arrange setup. And this is what is called a hierarchy problem, and we'll touch base with it later. Okay. These Higgs waves, what was the excitement about a few years ago with the Higgs, with Higgs? Okay. Well, just like the electromagnetic field has photons, the weak nuclear force fields have W bosons as the quantum particle that makes them up. Higgs waves, the Higgs field, has particles that make it up, and they're called the Higgs bosons. Okay, they also, so that the thing that was discovered a few years ago was that they also have masses of order 100 times the proton mass, so they live down here. That's the data. So one thing you want to do is, well, this is a great theory, but how are we supposed to test any of these ideas? And I want to tell you the machinery for doing these kinds of tests. It lies at the intersection of quantum mechanics and relativity, and the magic of these two things, which I didn't know when I got into the subject, it's just a free gift, is that with quantum mechanics and relativity, the rule of physics, it's easy to remember. Anything is possible to make. Okay? Anything is possible to make. Anything. With some probability. Okay? There's only one price tag. And that price tag is energy. Okay? And the mantra of, how you do this is simply E equals mc squared. Okay? Rightfully a famous formula. And you have to plug in, the input is enough energy. How much energy? You have to take the mass of the thing you would like to create and multiply it by the speed of light squared, which is to say a big number. And so if you just have a lot of energy concentrated, you can make anything. How could you make anything? I mean, normally we think maybe we can smash things together, and that's a very energetic thing to do. But if the thing you want to create is not there, How do you do it? You can take stone and sculpt it into something interesting, but that's because the stone is already there, and all you're doing is changing it a little bit. What's this business of creating something that's not even there? How can you do that? That's magic, but that's also the real world. And the way you do it is you take the thing you want, you bring it from the future, and release it after that, okay? And then off it goes. Now, you say, I haven't heard that one when I was reading Scientific American, the idea that you bring the thing you want from the future and set it go. Now, if your brains work, if your minds work, your memories work in thinking into the future from the past, mine doesn't, but if yours do, then what I'm really saying is that you can create anything you want as long as you create a kind of partner antimatter. Okay? You want a chair, you're going to have to create a certain amount of antimatter that goes with it. The antimatter is the thing brought from the future back into the past, but in the way our brains process it, it is antimatter going off in the future. Okay? So you can do it with some probability. I don't say that the probability is big. It depends on which process. But it's not zero. Okay? And so, great. You want to see Higgs bosons? Make them. Even if you don't have anything there like that, if it's not sitting inside the table, it's okay. Just make it. Okay. So, what do you do? This is how particle colliders work. They are the devices of magic. Okay. What you do, so here's an example of what's done at the Large Hadron Collider. You collide proton beams traveling very near the speed of light. They're very energetic, and they collide, and that's the E in E equals mc squared. It's big, it's concentrated, and there's some probability. The experts know how to work out the probabilities. I'm supposed to. I teach it, but I probably flunked the exam right now. Anyway, so you can create things like in the 80s, they created the W boson. Okay, it wasn't sitting inside the protons. It's just made by this magic. And the W boson is not a stable particle. It's a short-lived particle, like radioactive isotopes or something. It decays. So it decays into these nuclear jets. And then you have rigged a set of detectors, very sophisticated detectors, to pick up these nuclear jets and see that the debris is due to this kind of a W boson. And then you can tick this off and say, we discovered it, just like the Standard Model theory said we should. Similarly, in 2012, Higgs bosons were discovered in this way, and they're also short-lived. They live for a while, and then they decay into a pair of, say, photons, and then these photons are detected by these detectors, and again, we reconstruct that we have had a fleeting existence of Higgs bosons. So here's the Large Hadron Collider depicted far under the Franco-Swiss border, far underground, a kind of racetrack for these proton beams. Okay? And then there are special collision points at which underground there are these absolutely mammoth detectors. You can see they're mammoth, like that is a human inside the Atlas detector. So these are both enormous, but they're also the most sophisticated cameras in existence. And inside there, here's some collision, lots of stuff, but there are also here these two photons that are the telltale sign of a Higgs being created and then decaying. And by looking at it's a bit hard to see, but I'll just say it. Looking at the distribution of photon energies, there are various sources for producing photons at the LHC, most of them boring by the standards of this talk, but then there's a little bump, a little excess due to the fact that the Higgs boson happens to have a mass which produces photons with an energy E equals mc squared at a particular value of that mass, okay, 100 times the proton mass. So this is how discoveries are made in our subject. So one of the most basic questions you can ask in the field of particle physics or in the reductionist approach to science, for what it's worth, is whenever you discover what you think is the smallest thing, you ask, is there something smaller? Is it made of something, right? And you can see the history, you know most of it. The atom is named as the indivisible object, and yet here is the standard picture of an atom that you all know and love, and it's really a composite of electrons in a kind of microscopic quantum solar system orbiting the central nucleus. Okay? And then later we learned that the central nucleus is itself, there are various nuclei for the different elements, and the nucleus is itself a composite. It's secretly not an elementary object. It's made out of something, protons and neutrons. And some of you will know that these protons and neutrons themselves are, again, in turn, made of something. They are composites of these very interesting particles governed by quantum chromodynamics, quarks and gluons. And the quarks and gluons, well, actually, we don't know. As far as experiments have told us so far by banging things together and trying to see what's inside, quarks and gluons are point-like particles, but never say never, right? It's actually worth testing. So that's the history of compositeness. Now, we have discovered the Higgs boson, and we can ask, is it composite? So without having any purpose in mind, it is due diligence of a particle physicist to ask, I just discovered a particle a few years ago, is it elementary, point-like, or composite? Some reasonable size with something inside it, okay, some constituents. But indeed, if it was composite, this would help to resolve the hierarchy problem, okay? The question of why the internal space is only a little bit oblate instead of being a perfect sphere. I'm not going to explain how that works. Just take my word for it that it would help to explain that, okay? So you might say we have lots of precedent about compositeness. We have all these theories, we've understood all these experiments with theory to go with it, and we understand compositeness pretty well. But it turns out that if the Higgs is a composite, it would have to be a kind of tightly bound composite of its constituents in a way that we have not seen experimentally before, which tends to be, since theorists like to cheat by looking at what the data says, we also don't understand it theoretically very well either. Okay? So if it's a composite, it's very challenging to write a composite theory of the Higgs. Okay? And yet we would like that to instruct, to direct experiments in some direction or another, to tell them what to look for, to corroborate. But there is an indirect way, an indirect approach, which again involves the fifth dimension, but the fifth dimension in a different incarnation from what I've talked about. So up till now, you could say that the fifth dimension, or the sixth dimension, or the seventh dimension that I've talked about, well, they might be real, but they might just be a kind of, it's like talking about the chocolates when you're teaching about numbers. They might just be the mathematical way, or a diagrammatic way of talking about mathematics. But here, I'm again going to come back and say, no, it might actually be real, but in a different way. Okay? And we have to start by some very, very basic property of composites that you know and love. So let's just see. This is the electron. As far as we know, it's a point particle, so I've drawn it as a point, as close as I can. It doesn't share the property I'm about to tell you. So here is a nice composite. It's the atom. And we all know it's really small, right? So we already know that this particular shape in our memory means it's something really small. So if I show it to you on the big screen like this, none of you thinks that this is actually the size, like this is what an atom is, right? You all think of it as something so small you probably couldn't see it with your eyes. Okay? Similarly, when I show you this picture, you all think, yeah, this is about, this is not the size of an actual car, maybe a child's toy car or something, but it's not the size of an actual car. But it's about 1/3 the size of an actual, the front of a car, right? We all think this is about the size of a car. But when I show you this picture, you just think, oh, that's okay. It's probably a car a little further back. Okay? So shapes can give us a clue as to the size of the object that we're drawing. Okay? Shapes and sizes are correlated in the real world. This is always something really small, and this is always something man size. Okay, so in every public lecture, the lecturer is supposed to give the illusion of depth, and this is the part of the talk where I do that. Okay? But you know this illusion of depth. Okay? So here's the picture of the car, and I'm just drawing a funny shape. There it is. I'm drawing a funny shape, and I'm just making it bigger. And What's the illusion? Well, you can see it. The car seems to be heading towards you, but everything is just playing out on the screen. So this is the illusion of art, where by using characteristic shapes, I trick you into thinking that what is actually playing out on 2D is secretly 3D. Okay? This is what you're used to. Now, the amazing thing is that in most of the physics that we've seen in the real world, atoms have a characteristic shape, and things made of atoms have a characteristic size, and things made of atoms have a correct characteristic size. But theoretically, it is possible for there to be particle physics, which is what's called scale invariant. Okay? These are quantum systems in where the shapes that you can make out of whatever these theoretical laws of nature might be, the same shapes can occur on different size scales. So if I'm now using 3 dimensions to be represented by just the screen. So the screen represents 3 dimensions, okay? It's already 3-dimensional. And yet, there can be funny objects where if you make it, you can actually make it on a different size scale. You might say, yeah, I can build a small car and a big car. But if you looked in detail, you'd find that the size of every atom in the small car is the same as in a regular car. You can make a toy car and a big car. The toy car has atoms which are exactly the same size as the big car. Okay? But here I'm saying something more dramatic, that every atom of this little car is actually little, and every atom of this big car is actually big. Okay? And there's a way of squeezing them back and forth so that the link between shape and size has been lost. So that when something like this happens, when I take this small car and I release it in this world, in this theoretical world, and it, say, gets bigger, and then gets bigger, right? Well, you can't say, oh, that's an illusion of 3 dimensions. No, it's already I'm already trying to draw 3 dimensions on the screen. Instead, it's an illusion of a extra dimension of space, okay? So if you lived in a world like this, where objects and atoms can be shrunk in size and magnified in size, you would feel like you lived in a higher dimensional space, where you had a 4th dimension of space, which we of course call the 5th dimension, since the name 4th dimension is taken. And we call this piece of magic holography because of its relation. I mean, it's a similarity to the trick of holography that you might see on your credit cards. But basically, we're using physics in 3 dimensions, but weird physics, to fake living in a 4-dimensional space or a 5-dimensional space-time. Okay? So not only is, when you expand an object, not only does every atom rescale in length, but the time scales, like if you look at the clock in the small car, the clock will go tick, 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 tick. And if you look at the clock in the big car, which is a big clock, it will go tick, tick, tick. Okay? So it looks like in this world, when I come closer, right, in the 5th dimension, as I come closer to you, I also seem to slow down in my aging process for some bizarre reason. You might say, that tells me it's all a lie. That tells me the gig is up. You can't con me anymore, because a real dimension, if you just walk forward, you don't start slowing down the aging process, or we'd all be down the end of the room. So what's going on? And yet, we know that actually, if you're close to a black hole, the closer, if you've ever seen Interstellar, right? If the closer you are to a black hole, you actually age more slowly than if you're further away. In fact, the same is true in the Earth's gravitational field, but the effect is like a 1 in a billionth effect. So if you're here on Earth, you're aging 1 in a billionth times slower than if you were in a big balloon or in an airplane, if that's any comfort. But here it's a big effect. It's a big effect, just like near a black hole. And then the final little thing, you would say, yes, but you see, there must be something completely different about being, this dimension, this 5th dimension, which is a complete con, a complete fake. And then there's these dimensions, the usual 3 dimensions, which are real. Of course, I trust them. Of course, it's all real. And there must be some, but you can't really, in all my pictures, I have not, there it is. It's all being very facing you like this. Surely there's no ability to rotate freely between the fake direction and the real directions. Surely not. But amazingly, in the fusion of relativity and quantum mechanics, known as quantum field theory, you get for free in these scale invariant systems the ability to rotate from the illusionary direction to the true direction. So much so that we can no longer call it an illusion. In fact, you might say, if everything is actually sitting on the screen and two things go past each other, they'll collide, of course, right? And if you try to draw them, if you shrink one and try to pass it through, they'll still collide because it's all a fake, right? These two shapes are still going to collide. But amazingly, courtesy of this kind of symmetry, they'll pass through each other exactly as if there really was an extra dimension and they could pass by without having to knock into each other. So there's magic in this symmetry, and it means that the illusion cannot be caught out. And when an illusion or when a deception is perfect, we don't call it a deception. We call it in physics a duality. And this is the most famous duality in theoretical physics, and these are some of the most celebrated names in theoretical physics because of this discovery that such a fake was possible and can be reality. So in this way, these composite objects can pull off the illusion of a higher dimension and be equivalent to a theory in higher dimensions. I should say that for coming back to our theory of compositeness applied to the Higgs, there is a limit to how much you can squeeze things to be very small and expand them to be very large. And it's like a spring. I can squeeze it to be very small, but no smaller than when all the coils are actually touching. And that minimal size is called, in relativistic quantum theory, including gravity, it's called the Planck length, and it's about this size times the protons are much smaller than the proton size. It's the minimal size in quantum gravity. And if you let the spring go, it goes to some sort of natural size that it wants to be, and that is sort of, in composite Higgs theory, about a 10,000th or so of the proton size. So that means that instead of having a dimension that's created as an illusion that goes on forever, it's like there's a wall that you can't go past, and there's another wall that you can't go past. And so space-time looks like this. It looks like the picture I was drawing where the fifth dimension is an interval, not a circle, not an infinite line. It's an interval, and clocks behave funny in it, hence the word warped. So this is warped space-time, and 20 years ago we proposed, although we didn't know everything I just told you, we were just fiddling around. But anyway, we proposed that this was the natural sort of playground for particle physics, that this is the stage that particle physics should inhabit. It should be one with an interval-like extra dimension. And in the time since, we've understood what I've told you, which is that it's secretly a way of writing theories of a composite Higgs. Okay? And the theories look a bit like this. All the magic is in, the most important rule, real estate, or location, I should say. And so geography rules, but it's extra-dimensional geography that rules. Basically, all the different particle species, like photons, have a related field, the electromagnetic field in this case. The electron has its own quantum field, the electron quantum field, the Dirac field, as it's called. And so all these fields have slightly different profiles, or somewhat dramatically different profiles. Very naturally, they have, if you write a theory of this sort, they'll end up, different species of particles in different fields will have different profiles in the fifth dimension. If you're unaware of this microscopic dimension, you'd say they're all on top of each other. But secretly they live, some live on the East Coast, some live on the West Coast, and the basic rule is the people on the East Coast tend to talk more to each other, and the people on the West Coast tend to talk more to each other. And this kind of theory of interactions, based on locale, has a, even you take theories like this out of the box, they look a lot like what we see in the real world. The sort of pattern in which theories like this unfold macroscopically in terms of interaction strengths looks a little bit like the real world. So we take it sort of seriously, okay? In particular, here is how it helps to solve the hierarchy problem. So I've just erased some of the lines here. The Higgs happens to like to spend most of its time over here on the East Coast, and the graviton here on the West Coast. The Higgs is critical in making sure that the W boson, this oblateness issue, gives the W boson its mass. And of course, this fact that the Higgs does not overlap with the graviton very much means that the mass that the W boson gets through this oblateness is not gravitating very much. Now, if you know what kind of object doesn't gravitate very much, it's a light object, okay? And that's why the W boson in this picture comes out to be very light compared to sort of the theoretical maximum for any particle mass, which is a Planck mass, okay? So there's a connection of these overlaps and the funny geometry here with the way in which the hierarchy problem is understood, namely why particle masses are way down here when they could have been up here, okay? Okay, so we'd like to test a theory like this, okay? So we obviously need extra-dimensional perception, and I bring back the picture that I'd drawn at the beginning of an interval. So now we're zooming out, we're on macroscopic scales, this very tiny little interval in which we all live in this sideways direction, right? But the problem again was we need ultraviolet light. We need some very, very small wavelength light, which is outside our visual range if we're to detect this. And the dirty secret of quantum mechanics, which was one of the ways in which quantum mechanics was discovered, is that even a single photon of light, if it has a very small wavelength, you need a lot of energy just to have that photon, okay, to create that photon, to look around here, just one photon to look around. You still need, the smaller the wavelength, the bigger the energy you need, okay? They have a reciprocal relationship. Indeed, in this game where we're talking about zooming in here and we have this warped setup, this sort of warped light wave, or a single photon of the warped light wave that you would like in order to see inside this little cavity and say, yeah, there it is, the fifth dimension. It requires so much energy that you actually need the Large Hadron Collider to blast protons together, not photons, blast protons together in order to give the energy to create one of these warped photons, okay? These photons, they're banging around between these walls, which are like mirrors. The light goes back and forth, back and forth, back and forth. And the light doesn't, like most, light going into your eye, it splatters in your eye and the light's gone, but you have the signal in your head at some point. Here, the light goes back and forth. Before anything gets to your eye, it actually splatters against this wall and turns into things which also live near this wall on the East Coast. It turns into top quarks, a very exotic kind of matter. It turns into top quarks. The top quarks themselves are unstable. They turn into nuclear jets, and everything flies towards the LHC detectors. And that's the way we look for it. We look for evidence of this photon being created by the energy of the Large Hadron Collider. And so these are searches that have been done. This is a fairly early search in the history of the LHC, but it's an easier plot for me to explain. Here we're plotting top quark production at the LHC. On this axis, we're plotting the energy of top quarks that are being produced at the LHC. And basically, most of this picture is just saying that the more energetic the top quarks, the fewer of them are produced at the LHC. And most of this production of top quarks is actually just due to standard non-extra-dimensional processes, things that we understand pretty well, and are not due to the thing that we would like to see, which is looking in the extra dimension. If there had been, and there's data here as well, there's theory, which is this sort of curve, and there's data, which are the black dots. But in this little bit of green here, this little bump is what would have been the data That should have been the data if there had been a extra dimension of a certain size, okay? 1/1000th of the proton, 1,000th of the proton radius. If that was the size of the extra dimension, we should have seen a little bit extra here. And it could have been due to photons in the extra dimension, it could have been due to gravitons in the extra dimension, or it could have been due to gluons in the extra dimension. All of them are good ways of looking in the extra dimension. But we didn't see that extra excess. But I'm just pointing it out to you to say how tough it is, because you have to make sure you understand what theory predicts, and you have to make sure you understand what the experiments are actually seeing to even make this plot. And then you have to say with confidence, yes or no, whether you're seeing this little bit of extra stuff. Okay? So it's a tough game, but these searches are being conducted as we speak. So there is another body of experiments that I'll just say are out there, which is to not look at super high energies, but to try and look at many decimal place precision, and to look at things like Higgs boson properties, sort of chameleon-like processes where particles change species, or processes that look different when you play the movie backwards or forwards. Okay? These are all very powerful probes of theories like the kind I'm talking about, composite Higgs, or this kind of warped fifth dimension. But we are yet to make any kind of a discovery. But this is sort of the template for what we need to do. And there are even more powerful colliders and even more precise colliders, even measure even more decimal places that are being proposed in China, as well as at CERN, the laboratory which already hosts the Large Hadron Collider. Okay. I think I am, well, I have to say this and then I'll stop. I think this is fast. This is fast. I just wanted to say that it's not all physics at colliders. In fact, if I got through the whole thing, I would point to a variety of things. But let me just say this. Everybody knows the universe is expanding. That's because space is dynamical and it's really stretching. On the largest scales, it's just very uniformly stretching. And galaxies, which are sitting in this space, are just getting pulled apart. Okay, so we know that. There's the cartoon. Okay, but if you run the movie backwards in your heads, then of course things, instead of getting further and further apart, they would. If you run the movie backward, they'd be getting closer and closer and crushed, and eventually the galaxies would not be there, right? And stars would not be there. They would have disassembled. Everything would have been crushed to such high densities and high temperatures that you would be in a thick, opaque, and very hot cosmic soup of, even atoms wouldn't be possible. Only a soup of subatomic particles and antiparticles. That's it. That, presumably, is what our early universe was like. And it's interesting to see what this warped 5D spacetime would have been like under those conditions in the very early universe, when the temperatures were very high, very soon after the Big Bang. Instead of having our usual picture of two boundaries of the extra dimension, one of the boundaries gets replaced by an event horizon, which is extended in 3 dimensions, but at some particular place in the 5th dimension. Okay? So the second boundary is gone. It's been fried in this high temperature setup, and you're replaced by this event horizon, very much like a black hole event horizon. And it is veiling, it's covering up the place where the Higgs likes to live on the East Coast. Okay? It's like the East Coast got swallowed by a tsunami or something, right? Or it came out of the waters, but in the distant past it was underwater or something. And that's the thing it's the Higgs that is at the key of separating the weak from the electromagnetic forces. So with the Higgs covered, the electroweak force is actually intact. It's a dinosaur that was walking around in those days. The ancestor force, okay? Now later, as the universe expands in 3 dimensions and cools a little bit, then you find bubbles of these sort of 3-dimensional bubbles, not 2-dimensional bubbles, 3-dimensional bubbles of the second boundary starting to peek through the horizon, okay? And these boundaries can collide and they can move around and they can emit gravitational waves in 3 dimensions. And these bubbles are very much like when you're boiling water or your water goes through the right temperature, then you form bubbles, and that's what's happening here. It's what's called a phase transition. Sorry. And today, when the universe is very cold, all these bubbles have come together and joined up, and the horizon, the event horizon is gone, and you're just left with the picture that I originally showed you, where you have two solid boundaries. The Higgs is there, and if the Higgs is there, the W and the photon have been separated a little bit, the sphere has become oblate, and the two forces have been born from their single parent. Okay? And I'll just say this, I think I have run out of time. So I'll just say that you might say, yes, gravitational waves were emitted 14 billion years ago when all these exciting things were happening at the birth of new forces. What good does that do me now? And the answer is, I'll say it fast, that the gravitational waves emitted at that time, 14 billion years ago, if we just look very far away, they've taken 14 billion years to arrive on Earth. And we can build detectors like the LISA gravitational wave detector proposed to be built in the next decade or so. And we can look for the evidence coming from us in all directions of gravitational waves from 14 billion light years away, telling us something about this phase transition, the bubbles that were giving rise to the gravitational wave. Okay, I'll stop there. I'll just put the conclusions and let you read them, because I don't think there's any surprise there. I'll stop right there. Thank you.
Okay, questions?
Thank you. That was really very good.
Thank you.
But I didn't get the part where
That's a good start.
where the fifth dimension decreases the parameter sensitivity in the standard model.
So it's actually so indeed. I'll just say a word about it, because you didn't get it because I did not say it. But I can almost do it right now. There. It's all about these clocks. So this discrepancy says that the graviton, which lives more on this side, right? Gravitational forces also, this notion of how clocks behave or how time behaves is very closely related to energy and through E equals mc squared to mass. Okay? And this discrepancy, or this very sharp difference between the rate at which clocks tick here and clocks tick here, gives you a kind of that, let me say it like this, that if you take something that is sort of that weighs Planck mass here, and you move it over here, the same effect that makes clocks tick slower also makes the Planck mass object weigh much less. It is again a kind of a weird behavior that you would have even if you go near a black hole horizon. And this slowing of the clock is very much like going near a black hole horizon. So it's the thing that is not drawn here is the bizarre geometry of this curved space-time, the emergent curved space-time, warped. The warped is saying there's some weird geometric story here. But that geometry has this funny feature that clocks slow when you take them from here to here, but also Planck mass objects become much lighter when you move them over here. And the fact that the Higgs robustly can live on this side, which is the origin of giving masses to the W, is the key to how the W ends up much lighter than you would have expected. If the W boson, if the Higgs mechanism was playing out over here, then the W boson would have had the robust answer of Planck mass. So it's related to that. I won't say more.
Well, I think you may have just in the last sentence answered my question. I had thought that the hierarchy problem was one of a tuning.
Yeah.
And it seemed to me that you were saying that this innovation of the warp space and the scale invariance and so forth, it seems that it helps establish the mass of the W's. And I don't see how that's related to the tuning, if you understand what
Yes, I do.
was, yeah.
So the statement with regard to the tuning, so the tuning is the hierarchy problem even comes to exist when you study quantum effects in the standard model or theories of this sort. And you find that if the Higgs boson lived in the same place as the graviton, then naturally, without having to tune the parameters very carefully, the W boson mass would have been of order the Planck mass. It would have been nearly a black hole. But you could have tuned the parameters very carefully. I could make a needle stand on its head very carefully, and that would have allowed the W boson mass to be much lighter. It would have been a very delicate arrangement, but it would have been possible without any fifth dimension. That's true. On the other hand, the statement is that if you move the Higgs boson to live on the east coast here, that even if you change parameters or you kick the theory a little bit, that rather robustly the W boson mass is automatically small because of this, at the root of it, because of this funny warping that changes the rate at which clocks tick. Yeah.
Just going more with the whole thing about like the east and west side and the chart that you had that had the particles and their paths, and you said that the particles that had more similar paths would interact more. What exactly determines the shape of those paths, and what do those interactions look like?
Very good. So I did say that a sort of typical theory, you don't look at the data, you just take a theory of this sort out of the box, and typically the different fields will sort of distribute themselves, will have profiles in seemingly, radically different ways. And in one of your questions is, who decided that, right? And so all of these different fields have their classic equations that go with them. They're very tightly, the grammar, there are some choices you can make, but the grammar of what you're allowed to do is very tightly limited by just these overarching principles, relativity and quantum mechanics. And so, for example, the graviton, that behavior is determined by higher dimensional Einstein's equations of gravity. The electron or the charm quark or the top quark, these are determined by the Dirac equation for matter fields. The W boson or the photon, these are determined by generalizations of Maxwell's theory of electromagnetism. So all of these equations determine what I'll call the proclivity or the tendency for these sort of distributions of the fields. And you should think of these profiles you're seeing as being like a quantum probability. It means that, think of this as a probability distribution, meaning it's more likely that I will be found on the East Coast, but occasionally I find myself, occasionally I find myself on the West Coast. So they're probability distributions, and it's just more probable that the Higgs and top will talk to each other, but it's not impossible that the electron will also talk to the Higgs and so on. So that's that picture, but they are determined by fairly robust equations that govern the different types of particles they are.
How dependent is the fifth dimension theory on superstring? Because I understand superstring theory is not doing well lately. Is that correct?
So the sense in which superstring theory is not doing well, so my own take, superstring theory is doing marvelously well. Now, am I a superstring theorist, you should ask? Do I have something to gain by that? No. I think I spent my life making fun of superstring theorists. And they were all smarter than me, and so they didn't care. Okay, but so I'm first trying to say no. I am not a self-interested person in this question, and yet I have to give credit where it's due, which is I think superstring theory is doing very well. Why? Because it's trying to come at the world from a funny direction, which is it takes principles that are experimentally rooted, relativity and quantum mechanics, and the existence of gravity, and it's saying, if I only know these principles, the equivalence principle of gravity, the speed of light is constant to all observers, and however you want to frame quantum mechanics, right? With very, very general principles. Just with this, could the world have been made any other way, right? That's the question. And it finds that it's, with some little human assumptions coming in, but trying to keep it to a minimum, you're led to something like string theory. And then you say, but did it get the mass of the electron right? Did it predict that there was a top quark? And the answer is no. Coming from those very, very few axioms, it's trying to see if it can get something like a thumbnail sketch of the world. And then, if successful, try to get all the details and so on. And it has gone a long distance over now a couple of generations of physicists. But if it has not managed to nail down every experimental detail and predict it and say, look, I could have said this and I can predict lots of things, I'm a falsifiable theory in a simple way, it's not a failing, it's because of its unprecedented ambition. It is not possible in biology to just say, look, I don't need any data. I just have a few principles. There's a theory of evolution, right? There's a Darwinian selection. And now I'll just tell you what you're going to see. Okay? There's no other subject that attempts that, and rightfully so. But the grammar of relativity and quantum mechanics is so tight that you could almost hope to play that game. And so that's where string theory is basically trying to go. And by that standard, it's had enormous successes. And many of the ideas which are not sharp predictions have nevertheless been remarkable mechanisms which have been adopted by people who are not string theorists like myself in grappling with real data. So it's inspirational as well. So in this nuanced sense, I would say string theory is alive, well, and doing what it ought to be doing. We should just not hold it to some other standard. And it underlies some of my expectations. I mentioned it, but I was careful to separate what was theory from what was experimentally verified theory. I do distinguish those two. I'm not that far gone.
You mentioned earlier in the talk about if you wanted to make something, you could take it from the future and put it in the past.
Yes.
Well, if you look at the Feynman drawing of a positron,
right,
it looks like an electron going
yes,
backwards.
Exactly. That's exactly what I meant.
But we can't see that because we only go one direction in time.
Yeah. So
we're taking slices going in one direction.
Exactly. So I would say we do see it, and we just record the data so that we're not dragged off to the asylum. We tell our friends the story in a certain way. And I don't know if I can draw this here, but if this is time, and somebody says, I'm bringing a particle back, I don't hear. At time zero, there's nothing there. Maybe there's energy in some form, but it's not the thing I want. The thing I want is not here. What do I do? Well, here's a picture of somebody. I'm at least drawing what I said, right? I'm bringing the particle. I summon you from the future, and I let you go. Okay. Now, let's just play out second by second what is seen. And you'd say, okay, well, at time zero, all I had was some source of energy, but not the exotic thing I wanted. Then, at some later time, at some later time, there it is, I have the thing I want. There it is, right there. But, there's this other funny thing. It's funny in the sense that you can do the reverse of this. And suddenly, the thing you want and this other funny thing can disappear. But basically, there's the thing you want, and there's this other funny thing. The other funny thing is antimatter, okay? And then later on, the same thing, right? There's this funny thing and the thing you want. So this way of saying it, what you say is, I started with energy, and I created matter and antimatter, and then the two things separated. That is, that's still remarkable, because antimatter is pretty exotic. But this way of saying it does not sound insane. You can tell, in other words, it's the way you're telling the story like this is not the way we usually talk. We usually talk frame by frame, moving into the future, because this is our way our minds are constructed to stay sane. But okay, so I said it in a poetic way. By the way, the poetic way is the way you calculate. So, which is real, right? I said it the way that a physicist should think.